Hi, the doctor's in. I'm Dr. LB, and I'm here to help you through your math difficulties. Today, we look at roots of polynomial equations. If a polynomial has degree n, then it has n roots. Now, some of them may be repeated, but it has n roots. We can also say that if a complex number a plus bi is a root, then its complex conjugate a minus bi is also a root. This is very important for us because knowing one is a root means, hey, we have two complex numbers who are roots. The fundamental theorem of algebra states that if f of x is a polynomial of degree n, where n is bigger than or equal to 1, then f of x equals 0 has at least one complex root. Now, it doesn't mean that it's a complex number that what we think, but it could be a real number. Remember that real numbers are complex numbers as well. 4, it is a natural number. 4 is a whole number. 4 is an integer. 4 is a real number. But 4 is also a complex number. It is 4 plus 0i. So at least one of our roots will be complex. So the linear factorization theorem tells us that if we have an nth degree general polynomial, it can be broken down as this a sub n, which is the same leading coefficient that we have in the general polynomial, and it's x minus c sub 1 times x minus c sub 2 all the way to x minus c sub n. So it can be broken down into n factors where a sub n is the leading coefficient in front of those factors. Let's look at an example. We want to find an nth degree polynomial satisfying the following, where the degree is 3, x equals 4 is a root, and x equals 2i is a root. And f of negative 1 equals 50. Now, we're going to need that f of negative 1 equals negative 50 in order to find our a sub n. So, the polynomial would look like f of x equals a sub n. Now, knowing that 4 is a root means that x minus 4 is a factor. Knowing 2i is a root, we can take that across the equal sign. X minus 2i is a factor. Now remember, we just had a theorem that said if a complex number is a root, then its conjugate is also a root. So x minus 2i is a root. If we take the negative 2i across, it becomes positive. So x plus 2i is a factor. So let's clean this up a little bit with these factors, because remember, we're trying to get a general polynomial. Let's multiply together these two factors from the complex roots. We have x times x is x squared. The inner and outer terms on complex conjugate should cancel out. And we have minus 4i squared. Now remember that I squared is negative 1, so it's going to make this x squared plus 4. When we use FOIL on x minus 4 times x squared plus 4, we'll get x cubed minus 4x squared plus 4x minus 16. So we have something that's looking like what we need, but here now we need to use that f of negative 1 is negative 50. So in this case, f of x is negative 50. And everywhere there's an x, I'm going to put a negative 1. Negative 1 cubed is negative 1. Negative 1 squared is positive 1, but times that negative 4 is negative 4. Negative 1 times 4 is negative 4. Then we're going to subtract our 16. So we have negative 50 equals negative 25 times a sub n. So a sub n is going to be 2. So what this means for us is we're going to go back here f of x is going to be 2 times x cubed minus 4x squared plus 4x minus 16. So we have 2x cubed when we distribute minus 8x squared plus 8x minus 32 being our nth degree polynomial. Let's look at another one. Here, n is 3, x is negative 5, and x is 4 plus 3i. So we know that x equals 4 minus 3i is also going to be a root. So we have f of x equals our a sub n. X equals negative 5. If I take that over, it becomes x plus 5. Then I have x equals 4 plus 3i becomes x minus 4 minus 3i. And x equals 4 minus 3i becomes x minus 4 plus 3i. Again, we're going to go inside and we're going to look at these complex numbers. We're going to multiply those first. And what we're going to do is we're going to group our x plus 4 together as our first terms. And then we're going to look at the I portion as our second term. So x plus 4 times x plus 4, x minus 4 times x minus 4 is x minus 4 squared. If I do x minus 4 times a positive 3i and x minus 4 times a negative 3i, that cancels out. And I have 3i, negative 3i times 3i is negative 3i squared, negative 9i squared, which becomes plus 9 because remember, I squared is negative 1. So let's clean this up a little bit. We can expand out x minus 4 quantity squared. It's going to be x squared minus 8x plus 16 minus 9. Remember, you have to write them out side by side and use FOIL. When we clean that up a little bit, we're going to have x squared. It should be plus 9. We're going to have x squared minus x plus 25. And then we're going to need to use the distributive property. We distribute our x through, then we distribute our 5 throughout that second polynomial. So we're going to get x cubed minus 8x squared plus 25x plus 5x squared minus 40x plus 125. And this reduces down to x cubed minus 3x squared minus 15x plus 125. Now let's find a sub n. Remember here we had f of 2 being 91. So 91 equals a sub n. If I put 2 in here, I'm going to have 2 cubed minus 3 times 2 squared minus 15 times 2 plus 125. And what I get is 91 equals 91 a sub n. So a sub n is going to be 1. So I come back here and my f of x is 1 times this x cubed minus 3x squared minus 15x plus 125. And this is the nth degree polynomial that we are trying to find. So remember that Dr. LB is always in. Please come back for more math help.